All right, welcome to the second type of growth, and that's logistic growth. You probably just watched Exponential Growth, and we had lots of zombies and scary stuff. This time we get some hedgehogs and some hippogriffs. It's a much happier day. Now, the difference between exponential and logistic growth is pretty severe. Exponential growth is basically assuming that you could grow something with no restrictions whatsoever. There's no food restrictions, no size restrictions, nothing. Logistic growth is a little bit more realistic, and it takes into account the fact that there are probably uh, limitations to the amount that something can grow. Now, we're going to talk about logistic growth a little bit more holistically. We don't do as many calculations with this one as we do just kind of thinking and running with it. So if you have a differential equation of the form dp dt or dy dt equals kp times the m minus p, the solution curve is a function of this form. Now, I have to admit, you should memorize this p equals form. I've seen it on an AP exam, I think once, so it's not that important that you memorize it, but if you do memorize it, it makes your life easier because trying to rearrange to get it is incredibly difficult. But you should also memorize this form and just the idea that logistic growth and exponential growth are relatively similar. Logistic growth kind of starts off with that exponential growth piece right here, the dp dt equals k times p, but it also has a parentheses next to it with m minus p. Now, what are all these things? K is your growth constant like it was before. P is your current population. M is your carrying capacity, and this is the maximum sustainable population. It's not the maximum population, it's the maximum sustainable population. All right, so if you have, like a fence that can only hold 100 pigs, you could put 160 pigs inside. It's just that some of them are going to escape because they're going to climb on the backs of the other ones. So again, it's your maximum sustainable population. And then A doesn't come into play until you deal with the equation here. Capital A is like a random constant that you'll have to use an initial condition to solve for. It doesn't, I'm sure it has some meaning, but not in the context that you'd want it to. A is just a constant that you solve for. Now, slope fields for logistic growths are other things that you really should be able to figure out here. A slope field for a logistic growth model is shown below. All right, now, I feel like there should be some stuff next to this, and I'm not sure if it's my file or if it's the file you guys have in front of you. Nope, it looks like your file is missing things too, so we'll just write it in. The slope field for logistic growth model is shown below, and the reason I put this on here is because basically what I'm getting at here is if you start off with a population of 1, and I follow the slope field, it's going to do something like this. It's basically going to increase rather quickly until it reaches some value and then say, you know what, this is about as many as we can hold, we're going to level off here. Conversely, if you said, all right, I can hold about 4 things, but I put 6 inside, this is going to level off at 4 as well, but it's going to decrease in the beginning. So if P of 0 is greater than M, in other words, if your initial population is greater than your carrying capacity, then dp dt at t equals 0 is going to be negative. If you start off with a population higher than their carrying capacity, the initial rate of change of the population is negative, and honestly, it's not just negative in the beginning, it's always negative, because if you look at this coming from above, pardon me, sorry about the cough there. If you don't remember this about me, Mrs. Vibber has a dog and 2 cats, all of who are named after math or calculus. My dog Libby, also named after Leibniz, just climbed up on the bed, shook her fur, went everywhere, and went right down my throat. So I apologize for the coughing fit. Now Libby is happily sleeping, and I can get back to work. Anyways, if the initial population is greater than the carrying capacity, your slope field is going to always have a negative slope. And dp dt is always going to be negative. If p of 0 is less than m, then dp dt is always going to be positive. We're going to come up and then level out. Okay? All right. Now, looking at this picture here again, you can identify your carrying capacity because that's where that horizontal asymptote is. And again, your carrying capacity is the maximum sustainable population. All right, so what do we have to do with this? Honestly, logistic growth equations are very easy to work with. Look at the adorable hedgehog. He's so cute. So the rate of growth for hedgehogs in a hedgehog farm is the P to T equals blah, 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 4P times 120 minus P. All right, so this is K, that's your growth constant. This is M, your carrying capacity. What is the maximum sustainable population of hedgehogs? Well, that's your carrying capacity. That's 120 hedgehogs. Evaluate the limit as t approaches infinity of P of t. Well, you might be thinking, well, I don't have an equation for P. I just have an equation for dP dt. Well, that's all you need. Think about this limit holistically. The limit as time goes to infinity for the population of hedgehogs. How many hedgehogs should there be for eternity? Well, that should be 120. That's your sustainable population. Then what's the limit as t approaches infinity of dP dt? All right, so maybe you're thinking, well, okay, I can use this equation, plug in t equals infinity. Well, dP dt doesn't have a t in it. So how do I plug in t? Again, think about this holistically. What's the slope of the growth rate as t approaches infinity? Well, let's look at our slope field for that. If I come up here and t is approaching infinity, what's the slope along that asymptote? Well, my slope's approaching 0. Once I approach my sustainable population, I'm just going to stay there. I don't have to worry about my slope anymore. Thus, dt goes to 0 as t approaches infinity. All right, for what value of p is the population of hedgehogs increasing most rapidly? Well, we can solve for this, but I'm going to save you some time. Let's think about that for a second. If I have a growth rate and I'm dealing with a population, if I only have a couple hedgehogs on the farm, they're going to reproduce, but rather slowly. If I have a lot of hedgehogs on the farm, they're going to reproduce very quickly. But if I have too many, they can't reproduce as quick because they're missing some food that they need. Hold on, my 4-year-old needs me.
Hi, everybody.
That was my 4-year-old. He really wanted to say hi. Everybody say hi, Landon. Hi, Landon. All right, Landon's going to play Mario Super Sluggers while Mommy finishes this. Sorry, guys, I'm back. So, we have the rate of change is going to approach 0. And then we were talking about what value of P is it going to increase most rapidly. Long story short, as I was going into this, that's going to be 60. And contextually, that makes sense. Contextually, that makes sense because we need enough hedgehogs to reproduce, but not so many that they're reproducing beyond the carrying capacity. So at half the carrying capacity, that's when you're going to increase most rapidly. Okay? And then write an equation for the population of hedgehogs. If initially there were 4 at the farm, now we get into that P of T thing, and it's a really obnoxious way to go. So just kind of stick with me here. But basically we have P, we have P equals that yucky formula m over 1 plus ae to the negative mkt. So if initially there were 4 at the farm, and we have to deal with this equation, we are going to say there were 4 at the farm whose carrying capacity is 120. 1 plus ae to the negative 120 k times 0, because I said initially there were 4 at the farm, which implies t equals 0. So this is going to go to 1. So I have 4 equals 120 over 1 plus a. Well, as long as my denominator is 30, I'm going to get 4. So a is 29. So my population is going to be 120 over 1 plus 29e to the negative m, which is 120, k, which was given in front of the p and the 120 minus p, that's that 0.0004 number, t. And that ends up being, if you simplify it, p equals 120 over 1 plus 29e to the negative 0.048 t. All right, turn the page here. We're going to go into some sea turtles. So population of sea turtles has a differential equation of this. Remember, within here we have hidden k and we have m. Initially there were 8 sea turtles, so remember initially means that t equals 0. 8 sea turtles in the habitat. Evaluate the limit of the derivative and explain its meaning and context. Well, this you should be able to do based on the first one. The limit as t approaches infinity of dp dt is the same for every logistic growth. It's always going to be 0 because the rate of change of the population as t approaches infinity should be 0. It's going to reach that sustainable population and basically just stay there. Then as t approaches infinity of the population, it's going to reach the carrying capacity, and our carrying capacity over here was 200. Find p of t. This is just like the last one. So if there were 8 to begin with, 8 equals m over 1 plus ae to the 0, because I'm going to do mkt up here, and t is going to be 0, so I might as well just throw a 0 in now. So 200 divided by 25 would be 8, so a has to be 24. So I have p equals 200 over 1 plus 24e to the negative m, 200, k, 0.0006 t, which is going to be p equals 200 over 1 plus 24e to the negative 1.2 t. And then last but not least, find the value of t such that the population has reached 3/4 of its limiting value. So we're just going to say, all right, what's 3/4 of 200? That's 150. So I want to know what value of t solves this equation. And honestly, you could just put this in your calculator, cross multiply, solve. I'm not going to do all that just to save us a little bit of time because I think you could do that on your own. We get 3.564. Okay? All right, let's look at the next one. Population of rabbits is given by this, okay? Rewrite this equation in the other form. All right, well, why isn't it in that form now? 1,000. Oh, I see. There's no coefficient here. So I want you to rewrite this in the other form, and I take a moment to say this isn't necessary, just good practice. It's really because it's exponent laws, and I love exponent laws. So what we would do over here is we would say e to the 4.8 times e to the negative 0.7t. Hold on, I have to pause for my 4-year-old. Sorry guys, I'm back. So this e to the 4.8 and e to the negative 0.7t can be rewritten like this, and e to the 4.8 is going to be your a, and that ends up being 121.510, and e to the negative 0.7t is e to the, let's see, 1,000, because that's the m, times k, and k would then be that 0.7 divided by 1,000 t. So here's a, here's the other part. So p equals m over 1 plus e, or I'm sorry, a, e to the m k t. What's the maximum sustainable population? Maximum sustainable population, that's your carrying capacity, that's m, 1,000. What's the initial population of rabbits? In other words, what do you get? Pardon me, what do you get when t equals 0? Well, when t equals 0, I'd have 1,000 divided by 1 plus 121.510 e to the 0, which is going to be approximately 8. All right, turn the page. Yay, hippogriffs. This is happier. Take a second, try and do this one on your own. I think you can handle it. These aren't that bad. All right. Hopefully you hit pause a little bit here. What's the carrying capacity and the growth constant? Well, my carrying capacity is m, and m is 100. What's our growth constant? Well, negative 0.05, which is this exponent right here, is m times k. So that means negative 0.05, I'm sorry, it's negative mk. Negative 0.05 is negative 100k. So k is going to be positive 0.0005. So there's my k, there's my m. How many hippogriffs were at Hogwarts initially? So when t equals 0, this becomes 100. Sorry, I don't know why it keeps doing that. 100 divided by 1 plus 19 e to the 0. 5 hippogriffs at first. What's the differential equation for the growth rate of hippogriffs? Well, dp dt is kp to the m minus p. So it's going to be 0.0005 times p times m minus p. At what time did the hippogriffs reach half their carrying capacity? Well, our carrying capacity is 100, so we want to know when were there 50. So 50 is 100 plus 1 plus 19 e to the negative 0.05 t. Remember, you can swap these two, so I can say 100 divided by 50 equals 1 plus 19 e to the negative 0.05 t. 100 divided by 50 is really 2. Subtract 1, blah, blah, blah. Long story short, I don't want to waste your time as you're watching this video. You will get 58.889. And then last but not least, this is an old AP problem. I was only really able to find, I think there have been 2 in all the years I've searched, AP questions that actually have logistic growth and a free response. So I'm just going to go through and show you what it looked like. You got a population modeled by this. The way you know this is logistic growth is you have a P on the outside, a P on the inside, and a difference. But this should say M minus P. So the first thing we need to do here is get rid of the fact that that says P over 12. So I'm going to factor out a 1/12, which is going to make this 12 minus P, which is going to make the equation dp dt equals P over 60 times 12 minus P, or if you want to see it, 1/60th P times 12 minus P. So here's your growth constant, here's your carrying capacity. So if P of 0 equals 3, so if initially you have 3 in the population, what's the limit as t approaches infinity of the population? So if you start with 3, where's the population going to head? Well, it's going to head to the carrying capacity. If you start at 20, what's the limit of the population? Well, that means if you start higher than the population's supposed to be. It's still the same idea. They're trying to test you to see, does it matter if you start with 3 or 20? No, it doesn't. Your population still goes to your carrying capacity of 12. Coming back to if P of 0 equals 3, for what value of P is the population growing the fastest? It's growing the fastest when it's half of its carrying capacity. So that would be 6. A different population is modeled by the function y that satisfies the separable differential equation. We did those with slope fields right here. Find y of t if y of 0 equals 3. So this is asking you to do separation of variables, get it in a y equals, using the initial condition 0, 3. So hit pause, try and separate the variables and solve, and then come back. Assuming you did that, welcome back. I'm going to come down here and separate the variables myself. So dy dt equals y over 5 times 1 minus t over 12. If I separate the variables, I have, let's see, I'm going to multiply by 5 over y and by dt. So the dt's gone here, the y over 5 is gone there. So I have the integral of 5 over y dy equals the integral of 1 minus t over 12 dt. This is going to become 5 ln absolute value of y. This is going to become t minus t squared over 24 plus c. And then if y of 0 equals 3, I'm going to solve for t. And if I want to solve for t, I'm plugging in 0 for t and 3 for y. All right. So we have, let's see, 5 ln 3 equals 0 minus 0 plus c. So c is 5 ln 3. So 5 ln, I don't need the absolute value anymore because y was a positive 3 to begin with, so I can drop that. T minus t squared over 24 plus 5 ln 3. I'm going to divide everything by 5. and get ln y equals t over 5 minus t squared over 120 plus ln 3. I'm going to switch to exponential form, so y equals e to the t over 5 minus t squared over 120, and I can pull this 3 down in front, and that is your equation. And then for D, it says for the function y found in part C, what's the limit as t approaches infinity? Well, as t approaches infinity here, pardon me, as t approaches infinity for part D, y equals 3e to the infinity over 5 minus infinity squared over 120. Well, which of these is going to be bigger, infinity over 5 or infinity squared over 120? Definitely this part. So this is really 3e to the negative infinity. E to the negative infinity is like 1 over e to the infinity. That goes to 0. So this limit as t approaches infinity of y of t is 0. And that's logistic growth. Much happier than exponential growth. No zombies, hippogriffs, and hedgehogs. Have a great day.